This meeting is being recorded.
Welcome everybody back to data mining. Let's see, we are in right now the topic 3 folder on the class repo, and a lot of upcoming assignment-ish stuff, assessment-y things in this class. So first thing is that tomorrow, Wednesday, we'll have the next quiz on the true, false, open stuff from chapter 1. There will be also on Sunday is when your finite hypothesis classes Jupyter Notebook is due. And then next Wednesday, we'll have this definitions quiz.pdf. Up here in front in the printouts, there is this quiz.pdf, which is the definitions. I think I have it open right here. Just all the definitions from chapter 2. So far we've talked about the dichotomies. We'll talk about, I think, all the other ones today. And then at the very bottom here, there's these things that I left off from the first chapter quiz. They're defined, and we talked about them in the topic 2 section about the finite hypothesis class generalization theorem and the Hoeffding inequality. So you will have to know those for that quiz. And then we will have another true false open quiz on the chapter 2 stuff that we're going over right now. And that will be at some point in the future, more than a week away. I'll just highlight that there is a lot of stuff due or things for you to study for, things to prepare for right now. I acknowledge that. And a little bit I apologize for that. It's always not fun having a lot of things due, things to work on at the same time. But I also just want to highlight about why that's the case, that this chapter 2 stuff here is all very hard. Again, this is the most mathematically challenging portion of the textbook. And it's because of that, it's easy to fall behind right now. And so I just want to have all of these assignments. The purpose of all these assignments is to help you make sure that you're not falling behind. The remainder of the material in this class is easier than the stuff that we'll be going over here in chapter 2, that we've started going over here in chapter 2. But it's also the case that if you don't fully understand the stuff from chapter 2, then you'll be struggling with the remainder of the material. So have all these assignments here, all of these quizzes and other things, assessments specifically, so that you will be able to master this chapter 2 stuff and then move on to less challenging, but still challenging material. I'll also say that I usually try to design the courses so that these sorts of heavy-ish weeks are in what are usually off weeks on other courses. So my sense is that a lot of students had midterms and things in the last week or two, maybe this week as well, but hopefully things in your other classes die down a little bit over the next 2 weeks here with all this stuff due. Yeah, trying to do my best to keep your workload balanced here. Any questions on anything administrative? Yes.
Yeah. How deep into the safe skip sections of chapter 2 should we go into?
The safe skip sections of chapter 2. So again, in chapter 2, I'll pull up my copy of the textbook right here so we can look at for a second. And there are these boxes here about the begin safe skip and the then end safe skip down here. These go into technicalities of different proofs. And you are not responsible for any of the material between those boxes. I will not directly ask you any questions about the material between these boxes, and I will not expect you to talk about the material between these boxes. Some people might find at least skimming this part useful to help maybe complete some of the steps of the proof. But that is a up to you sort of thing about what's useful for you. Does that answer your question? Cool. Good question. Any other questions so far? Okay. Last time, So again, there's notes printouts up here up front. What's printed out is this quiz.pdf and this notes2.pdf. We may or may not get to the notes2.pdf today. Last time we started on the notes1.pdf right here in the topic 3 about chapter 2. And we will continue today talking about this notes1.pdf up here. So this is the training versus testing chapter. And again, like big picture, where are we going? There's a bunch of these generalization bounds, theorems that bound the generalization error. Again, the generalization error, the difference between our out of sample error and our in sample error. And the whole purpose of these generalization bounds is to give us some insight on our out of sample error E out. Again, the E out is based on the true distribution of the data, something that we do not know and we can't know in principle. So it is never possible to directly measure our out of sample error E out. The in sample error E in, that is something that we can measure, we have access to. Vast majority of machine learning algorithms directly compute the in-sample error as it's learning the algorithm. But even if it doesn't directly compute the in-sample error, that's something that is still easy for us to mechanically calculate. And so knowing the in-sample error and knowing a bound like this, we can have some sort of result on our out-of-sample error. In chapter 1, or the between chapter 1 and chapter 2 sections, we talk about this bound right here, where again, M is the size of our hypothesis class. So this here, upside down. This M value right here is the size of the hypothesis class, size of H. I've written down all these things before. This is just a review, so you don't need to feel like you have to write down everything that I'm writing right here. But the M here, the size of our hypothesis class, and this is particular for the finite hypothesis classes. And we talked about those as the motivation for those is they're easier to understand, but we don't usually use those in practice. And the thing that we usually use in practice is an infinite hypothesis class. And what we're building up to is these theorems down here that use the VC dimension instead of M. The VC dimension we'll see is applicable for all hypothesis classes, and DVC will be finite even for some infinite hypothesis classes. For some infinite hypothesis classes. The actually understanding the definition of DVC, our VC dimension right here, is the whole point of this packet. And probably by the end of today, we will have defined the VC dimension right here. The one last note on this page here is the textbook gives us this bound right here, DVC log n divided by n. The best possible bound that is known and is also known to be the best possible is DVC over n. This is more technical up here. We will just be doing this bottom one in the textbook. This is what we are doing. So that is our goal right here. And again, the reason for talking about this is because it is the only tool that we have, the only tool that exists for understanding our out of sample error, which is the only thing that we actually care about when we are using these machine learning algorithms. Okay. Last time, we ended talking about this dichotomies definition right here. And the dichotomies, an admittedly very confusing thing. There's a lot of unintuitive things going on in this definition right here. And we did an example last time. We will do another example here sort of right now on the subsequent page. Again, though, the things to keep in mind here are the entries here, the things that are inside of our dichotomy. A dichotomy is a set, so the elements of our set, the elements of a dichotomy, these are entries in +1, -1, raised to the n power. So all the other sets that we've seen before have had a different structure than this. This is a little bit confusing. It looks like there's h's inside of here. It looks like it should be like this should be entries in r to the d, but they're not. The entries in this set are +1, -1 to the n power. And the purpose of putting this in the set notation right here is the set removes duplicates. Set removes the duplicates. And again, these notes structured to follow along with the textbook very, very closely. And so section 2.1.1, if you're still feeling like the idea of dichotomies, there's not fully clicking for you, this is the place in the textbook right here to look for that information. We're gonna go on today. So this next page right here, defining this thing called the growth function and doing this example 2.1 from the textbook. I'm gonna start with the example, doing a bunch of pictures and explaining things down here. And then once we've done that, we will come back up to the definition of the growth function up here and explain what's going on up here. So what I'm going to do is I'm going to draw some data sets. We're going to start with our, in all of these cases, the D will be equal to 2. The dimension of our data will be equal to 2. But we're going to start with n equals 3. N equals 3. 3 data points. And there's basically like 2 fundamental cases here that are going to be interesting to us. The first fundamental case will be when all 3 of those data points are collinear. So these 3 points right here sitting on the same line. Collinear, they all sit on the same line. And I'll call these points x1, x2, x3. We'll start on this case up here, but I will also highlight there's another important case down here that we'll get into next, where the data points are not collinear, x1, x2, and x3, all forming this sort of triangle shape. And between these 2 data sets, this sort of represents all the possible things that can happen on a in D equals 2 and N equals 3, no matter how you arrange the points, you're either going to have things sit on a triangle like this, or things sit on a line like this. And so we're only doing 2 examples, but this really captures like everything that can possibly happen. On the right-hand side over here, I'm going to write out these dichotomies, H of x1, x2, x3. Again, this is our notation of the dichotomy from the previous page. This H up here is the hypothesis class. And when we take a hypothesis class, which is a set, and we apply it to a handful of data points, this is sort of like an abusive notation thing where we individually apply these data points to all the members of the hypothesis class. The entries of this set are going to be, I'm going to scroll up just for a second so we can see the definition up here. The entries of this H hypothesis class applied to the data set right here, the entries of these dichotomies are going to again be these tuples where the length is in, the number of data points is in, and each entry is either +1 or -1. So coming down here, I'm going to draw all of the possible dichotomies of a hypothesis H on 3 data points. That would be everything is +1, or we have a -1 over here, or minus, plus, plus, minus, minus. Basically all of the combinations that are possible of pluses and minuses. So this is with everything where the first column over here is plus, and now where the first column is minus, repeating that, minus, plus, minus, 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 plus, and minus, minus, minus. And what we're going to do, so this, what I have on the right-hand side, this is all of the possible dichotomies that we could possibly get for a hypothesis class with 3 points inside of it, where we're applying these 3 points to the hypothesis class. And we're going to see which of these dichotomies can we actually realize using the perceptron on these 2 data sets over here. So as an example, we're looking first at this. Let's see, I'm in orange right now. So this is my orange data set. I'll call this capital X sub 1 for my orange data set over here. And recall that the perceptron hypothesis class is a straight line that we draw somewhere in our space of points. And so one possible perceptron hypothesis class would be this one right here. And in this case, I could put, say, the positives on this side over here and the negatives on this side over here. And if I do that, this hypothesis, I'll call it H1 right here, this hypothesis corresponds to X2 and X3 being positive. So X2 and X3 being positive and X1 being negative. So we have negative, positive, positive. That's what this H1 right here corresponds to, is sort of this row. And again, this is one of the entries in the dichotomy. We're trying to map out all of the dichotomies so far, all of the dichotomies that exist for this data set, and this is one of the entries of this dichotomy. We're going to see in a second some more entries in this dichotomy, but this is just one entry in the dichotomy. Again, the entries in that dichotomy are the same dimension as the number of data points, in this case 3, and each one of those dimensions is either -1 or +1. Any questions about where we're at so far? People tracking? Abika?
So this is more about the output of the hypothesis rather than like describing it.
So the dichotomy only cares about the output of the hypothesis. These are pluses and minuses over here. So these are, this is all possible combinations of outputs for different hypotheses in our data set. But the structure of the dichotomy itself is not dependent on the structure of the hypothesis class. No matter what the hypothesis class H is, the structure of this dichotomy of it being 3 entries containing +1s and -1s is going to be the same.
So this H1 notation is not referring to a hypothesis.
So this H1 right here, we have realized this entry in the dichotomy here with a -1 because H1 here is in fact contained in H. We've demonstrated that H1 right here is contained in H by drawing this line here, showing that there is some hypothesis. Like this is one of the valid perceptron hypothesis right here. And it is contained in H. If we have this as our hypothesis, then this is the particular set of labels that it gives to those 3 points. So the structure of our dichotomy over here does not depend on H, but the actual values that will be inside of the dichotomy will depend on H. So we've seen here so far, this particular row will in fact be contained in H because we have found some hypothesis that makes this labeling possible. Intentionally, as I'm explaining things, answering questions, trying to say the same thing in many different ways because there is a lot of different ways of saying these things, and some of them will maybe click for you more than others. I will also say that I have not met anybody, whether as a student or professionally researcher, who has found these concepts intuitive and where it was easy to like grasp them the first time that you see them. So yeah, it just takes a lot of practicing examples.
So when you're saying like H parentheses X minus 2 is an abuse of the because this is not my hypothesis, it's not the outcome of it, so that's what I mean by abuse.
So by abuse of notation, I mean it's defined right here where this is what H of X1 X in means is this thing over here. But normally when you see a parenthesis next to a thing, you think of a function, but this is not like applying some things to a function because the thing on the left over here, this H is not a function. This is a set. And the reason we're using function notation is because we are applying these values over here to every element of that set. So it's kind of like applying to a function, but it's not really applying to a function.
Are hypotheses that produce the same that is also like removed
Question is, are hypotheses that produce the same dichotomies removed as duplicates? And the answer is that, let's say here we have H1 contained in H. Let's say this is this line right here. This is another valid hypothesis in H, H2 contained in H. This is another valid hypothesis. And that also corresponds to this same labeling over here of these 3 data points. And so both H2 and H1 are contained in H, but they have the exact same like output over here. So the fact that this thing is inside of a set over here means that that duplicate output will be combined, smashed into just one output. Let's see, I'm going to do some more working through of all the different possible combinations over here, and that will hopefully also help clear things up for any lingering questions. So we have 2 hypotheses that we've drawn over here. We've seen that they give us the same combinations of output over here. And so this is one of our entries in the dichotomy. Another possible entry in the dichotomy would be the same exact line right here, the same exact line as H1 right here, but just labeling the pluses and the negatives on the opposite side. Plus and negative like this. Call that H2, or I guess we're already using H2, call that H3. H3 is also contained in the hypothesis class. And now H3 provides a different set of labelings. X1 will be positive, and X2 and X3 will be negative. So we go positive, negative, negative, positive, negative, negative. That's this right here. And so that corresponds to the H3. When we're computing these dichotomies, we need to consider all possible combinations of our hypotheses. So consider every hypothesis in the hypothesis class. And we kind of already mentioned here that H2 and H1, they give us the same output over here, that they're basically the same thing. For the purposes of this data set right here, the green line and the blue line are the same thing because they give us the same output. So there's really only 3 lines here that are meaningful for this data set. And we've already drawn one of them right here between X1 and X2. The other line that's meaningful for this data set is separating X2 and X3 like this. We'll call this H4. And H4 could be, we'll start with positive on top, negative on bottom. So X3 is positive, X1 and X2 are negative, X1 and X2 are negative, X3 is positive. That's this row right here. That will be H4. And we can reverse the labeling over here, put negative and positive like that, call that H5. And now X3 is negative. X3 is negative, but X1 and X2 are both positive. So this right here corresponds to H5. And the last of these important lines, the last of these possible lines would be one that is outside of all the data points like this. And here, if we put positive on one side on the top and negative on the bottom, that gives us positive labels to everything. So that would correspond to this right here. I'll explicitly call this H6. And I'm running out of colors, so H6 and H5 have the same color right here. But H6 here labels everything as above it as positive. All the data points are above it, so all the data points are positive. And then the very last line would be H6 reversed with negative up above and positive down below. And if we do that combination, then we get negative for all 3 of the data points, X1, X2, and X3, all negative down here, like that. And we'll call that H7, the orange version, H7. In this case, for this particular data set right here, for this data set on the left-hand side, where the data points are collinear, in this case, it is impossible to get these 2 values right here. Impossible to have the X2 data point have a different label than X1 and X3. For X1, 2, or X2, sorry. X2, X2 to have a label different from both X1 and X3. So because of that, these two entries not in the dichotomy. Not in the dichotomy, not in the dichotomy. Everything else is in the dichotomy. So on this data set right here, the size of the dichotomies of H for the perceptron hypothesis class would be 6, because there are 6 entries here that are included. All of these entries have many different hypotheses that can generate that dichotomy. H2 and H1, again, they generate the same element in the dichotomy right here. There's going to be an infinite number of pairs of hypotheses that line up to do this. But the important thing is that there are some things that we cannot generate, like negative plus negative or plus negative plus. There is no way to draw a single straight line through here that's going to separate X2 from these other X1 and X3. And so these two lines right here are not included in the dichotomy. So the size of the dichotomy in this case, the size of that is equal to 6. Yeah, go ahead. Yeah, so this dichotomy right here, we just talked specifically about this data set right here. Dichotomies are specific to data sets. So you have to have a particular data set in mind to talk about a dichotomy. The other data set down here, though, that is the other possible case of what can happen. This data set right here. Now, it would be possible to separate out X2 from all of the other data points. We could draw a line like this, and whether we put positive on one side and negative on the other, or negative and positive, we can separate out X2 from the other data points. It's possible to separate any of these data points, have whatever combination of class labels like we have over here. It's possible to achieve everything that we had before. Now it's also possible to achieve this middle balance. So this data set right here would have the size of the dichotomy, the size of H of X1, X2, X3, size of that being equal to 8, because it's possible to now divide everything and get all possible combinations of labels. Any questions? Yeah.
What does it look like for hypothesis class to be collinear, or like the groups of hypothesis classes to be collinear versus this triangle?
So just to be clear, here the data points are collinear. The hypothesis classes are not collinear. The data points are collinear. And so it's because of the fact that X2 sits on the same line as X1 and X3 right here that we can't draw a straight line that separates X2 from X1 and X3. If it was off the line in any small amount, forming some sort of triangle relation, then it would be possible to separate it out like that. Yeah.
Sorry, I missed this, but what is the NH3
Up here, the D equals 2 and N equals 3?
No,
So the question is, there's a bunch of text up here. How does that relate to the stuff that we're drawing down here? And the answer is, I'm going to use this drawing to explain that in a minute, but we haven't talked about this stuff in the text yet. Okay, so let's talk about this stuff in the text. So again, this definition here of the growth function, this is what's going to be very important for us for measuring how complex a hypothesis class is. One of the ways of interpreting this is the measure of how big the hypothesis class is. And big, you'll see big and complex both being used sort of as synonyms throughout the textbook here. So how big the hypothesis class is, or how complex the hypothesis class is. And the definition here is based off of the dichotomies. So you have to understand what the dichotomy is in order to understand this growth function. And again, the vertical bar right here, this is the set size, the vertical bar indicating the size of the set. Size of the set. And the growth function m sub h of n is the largest possible dichotomy that you can create on size n. So in this case, the growth function of n, mh of 3, mh of 3 would not be equal to 6 because we found a data set that had a larger growth function. We found h is equal to 8. The size of h here, the size of this dichotomy is equal to 8. And so it can't possibly be 6, has to be at least 8. It turns out that no matter 8 is the biggest in this case because whatever possible combinations of pluses and minuses you have over here, there are 8 possible combinations, 3 data points, 3 data points, each with 2 possibilities. Implies 2 to the third equals 8 possible entries in the dichotomy. 8 possible entries in the dichotomy. And so m sub h of 3, so keep going down here, applies mh of 3 is equal to 8. The most important thing here, the way that, I'll scroll back down in a second, but the way that students make mistakes with this growth function here is forgetting that it's the maximum over all possible data points. So just observing that one particular dichotomy has a particular size is not enough to determine what the growth function is at that size. You have to find the worst case scenario. What is the biggest possible thing? And in this case, we found a hypothesis, or sorry, we found a data set whose dichotomy has size 8, and that is as big as it could possibly be. And so the growth function is equal to 8 for n equals 3. Yeah.
Is there any n in which we can choose to
So the question is there any n for which the max is not going to be equal to 2 to the n? And this second problem down here has this as a fact. This is a thing that is true. M sub h of n will always be less than or equal to 2 to the n. That is a true statement right here. The problem here is asking for prove this or find a counterexample. So you know it's a prove thing now. There is no counterexample to this. The idea here is that the number of the dichotomies themselves, H is always a subset of the set of +1, -1 to the n. This H here, sort of again by abusive notation, that's intended to be the dichotomy H, x1, x2, ... xn. And this set exponential right here, that thing has size 2 to the n. So the size of your dichotomy is always going to be less than or equal to 2 to the n, the true thing. Did that answer your question?
like when we think on max size of the dichotomy, still for that specific data set, not for that.
So the question is, for a dichotomy, we're thinking about a specific data set, and that's true, but a specific data set has a specific n. So once you fix a data set, you have also fixed an n value up here. So this, let's see, so this is an upper bound on our growth function mh of n, and it will be the case that it is not always equal to 2 to the n. It is this inequality part here is important, that it is less than or equal to 2 to the n. And let's say I ran out of space up there, so there's nothing more to say with problem 2 right here. I'll draw a bar right here. What I'm writing down here is there's a continuation from the previous page. It's problem 1 on the previous page. And we'll do the next part of problem 1 said calculate the m sub h of 4 for the perceptron. And so we'll go ahead and do that, and we'll see that this is going to be less than 2 to the 16, or less than 2 to the 4, which is equal to 16. So here we'll put out our typical data set for, again, d equals 2, n equals 4. This would be the hardest possible data set. Call this x1, x2, x3, and x4. And what is hopefully reasonable to convince yourself is that no matter where you draw straight lines through here, you'll not be able to get the particular h here that you won't be able to get, h1, x1, x2, x3, x4. I don't want to write out all the possible combinations here because that's a lot of them, but the things that you can't get are x1 and x3 being the same and x2 and x4 being different. So you can't get plus, negative, negative, plus, or negative, plus, plus, negative. These two entries in the dichotomy, not possible to get. All the other possible combinations are achievable with the perceptron. We said there are the total number of combinations here is 2 raised to the power of n. So n equals 4. So total combinations equals 2 to the 4 equals 16. And there are 2 that we cannot achieve. So 16 minus 2 is 14, which is what m sub h of 4 is equal to. The reason why there's a minus 2 right here, why we're subtracting off the 2, is because that corresponds to these 2 possible combinations that we cannot achieve with the perceptron hypothesis class. So the minus 2 right here corresponds to these 2 combinations that we cannot achieve with the perceptron hypothesis class. Yeah.
But isn't that possible to just draw a line between x1 and x2?
Let's see, so
Like if the line goes down, one side is 1 and 4, one side is 2 and 3.
one side has, you're suggesting this?
Yeah.
So now x1 and x4 are the, thank you. So you are correct. The x1 and x4 are the same, x1 and x4 are the same, x3 and x2 are the same, x3 and x2 are the same.
Did you mean like x1, x3 or
Yeah, so this, I meant plus minus minus right here, minus plus, minus plus. So now the things that can't be the same are the x1 up here with the x3. Those 2 things cannot be labeled the same, where x2 and x4 are different than them. There's no way to draw a straight line through here that groups x1 and x3 together and separates x2 and x4 from that group. So I made the mistake. I lost track of my x3s and x4s over here and reversed those 2 positions. So for the way I drew this on the left-hand side, x1, x2, x3, x4 in this diamond shape, it would be plus minus plus minus and minus plus minus plus that cannot be drawn, that cannot be achieved. Thank you for pointing that out. Yes. Yeah. Yeah, so this is a good question here about, like I've shown for one particular data set here that we cannot achieve a dichotomy with size 16. But the question is, maybe there's a different data set of size 4 that would allow us to achieve a dichotomy of 16. And so what I've done here is I've not proved this statement. I've just sort of explained this statement, the intuition behind it. I've not proved it, just explained the intuition. There, at this point in the textbook, they follow the same pattern of not proving it, just explaining the intuition. At a later point, they will do this problem in general and do a proof for the general dimensions, where D can be arbitrary. So I guess the thing to capture at this point is just like the intuition here. You should maybe be able to convince yourself like that there's not really any other, like this is the hardest case where everything's not collinear. There would be other situations where things are collinear, but that only makes the things that you can't do smaller. But yeah, this is not a proof. This is just by example. Does that answer your question, Anne? Sort of? Okay. Let's see. So the, again, growth function, the thing to remember here, it's the worst over all possible data points of the size of the dichotomy. Lots of weird things going on here with that definition that just takes some working through some examples here to help. And again, the textbook has a little more examples that if you're missing something from what we're talking about right now, those examples can help. Go ahead, Marco.
Do growth functions follow any patterns as n grows bigger?
Say that again.
Do growth functions follow any patterns as n grows bigger?
Yeah, so does the growth function follow any patterns? And that's the right exact sort of question to be asking about this. And the answer is yes, they do follow patterns. What we will see here, let's go ahead and skip that. Section 2.1.2, this is the key theorem here about the patterns that the growth function follows. In the textbook, this is theorem 2.4. And we're not going to prove this theorem in class. We're just going to talk about like, what does this theorem mean? In the textbook, all they do for the theorem is state this part right here, that the growth function is bounded by this scary looking summation. But the reason why this is important is because this summation right here is upper bounded by a polynomial. And so what this theorem is saying is that if our growth function is not exponential, so if mh of k is less than 2 to the k, we already saw that growth function has to be at most 2 to the k. It's less than or equal to 2 to the k. So this means if it is not equal to 2 to the k, this condition equivalent to mh of k not equal to 2 to the k, then we're going to be polynomial. So this implies that our growth function is either exponential or it is polynomial, and it can't be anything else. It can't be anything between those ranges. It can't be anything smaller than polynomial, and it can't be anything bigger than exponential. This term breakpoint right here is defined in the page above. I'll scroll up in just a second and we'll talk about what that means. Okay, I'm going to scroll up now. So there's two definitions here on this page that are important, this idea of shatter and the idea of a breakpoint. So first, let's talk about shattering. There are three equivalent definitions of shattering that you'll have to memorize. Some of these definitions are easier to apply in certain situations, but I want to, in class, focus on the intuition behind shattering. So the focus on the intuition. So the intuition here is that when our data set was collinear like this, so again, the D equals 2, N equals 3, and we have the collinear data set. The perceptron hypothesis class does not shatter this data set. Perceptron does not shatter this data set. And that is because coming up to our definitions up here, the size of the dichotomies, if we take a look at part 3 right here, the size of the dichotomy was not equal to 2 to the n. In order to say that a hypothesis class shatters a data set, we have to have the hypothesis class equal to 2 to the n. And if the hypothesis class does not shatter the data set, then the hypothesis class size is not 2 to the n. So here we saw that m, or the size of h, the size of h of x1, x2, x3, saw the size of that is equal to 6, and that implies the not shattering. The other data set that we saw, the next data set that we saw with the triangle, this data set right here, x1, x2, x3. Here we saw that the size of this hypothesis class, or the size of this the size of this dichotomy was 8, x1, x2, x3, meaning that we can get all of the possible labelings. We can get all of the possible labelings here of x1 and x2 and x3. So this hypothesis class does shatter this data set. Our size 8 here, that's equal to 2 to the n. So that implies H does shatter X. Or the perceptron shatters this data set, H here being the perceptron data set. H shatters X, or equivalently, perceptron shatters X. And then the last data point that we saw with D equals 2 and N equals 4, the last data set here, the number of size of the dichotomy, x1, x2, x3, x4, that was equal to 14, which is not equal to 2 to the 4. So that implies that H does not shatter. Again, the intuition behind this verb shattering is that your hypothesis class is powerful enough to be able to assign any possible label to any combination of data points. And there are those 3 different equivalent ways of stating that up above. You'll be responsible for knowing all 3 of those equivalent ways of stating that. All right, yeah.
For the first statement, hypothesis
Mm-hmm.
I guess, like, what would be an example?
So one that can't generate it is this one down here, because it's we saw the plus minus combination, not able to generate that. Last definition-y thing here, definition 4, if no data set of size k can be shattered by h, then k is said to be a breakpoint for h. So here, n equals 3 is not a breakpoint. 3, not a breakpoint. Because this data set right here shatters the data, or the hypothesis class shatters this data set right here, which is of size 3, but 4 is a breakpoint. 4 is a breakpoint. And that's because there is no data set that is shattered by the perceptron in this case. So these two statements being equivalent to each other, it's a double-sided arrow right there. 4 is a breakpoint. No data set of size 4 can be shattered. And one simple property of breakpoints is that if data sets of size 4 cannot be shattered, then 5, 6, 7 also cannot be shattered. So 5 also a breakpoint, and 6, 7, 8, and so on, also breakpoints. Any number, if k is a breakpoint, any number greater than k is also a breakpoint. We already a little bit talked about this on the next page down below, but the reason why this is called a breakpoint, the semantics behind it, is because it breaks the exponential behavior and it changes the growth rate to polynomial. That if a number is not a breakpoint, then the growth function is exponential. But if the number is a great breakpoint, then the growth function is polynomial. Yes, Jay.
I have a question about what you said earlier.
Okay.
Something confusing when it comes to that the hypothesis class is powerful enough to make one a breakpoint, but it seems that this is how data is arranged in the hypothesis itself. So I was wondering what it means for the hypothesis.
Yeah, so this is a good question. The question over here is, I mentioned that this growth function is somehow like a measure of the hypothesis class. And then all these other things that we've been talking about as well, like breakpoints and shattering, those are all somehow like related to this growth function. But it seems like all of these things are like dependent on the data set. And so how is this like a property of the hypothesis class and not a property of the data set? And the answer is all buried in this max right here. This max is doing a lot of work because this max is considering over all possible data sets, how does the hypothesis class perform? So this is somehow thinking like a worst case scenario about our data sets. What is if there is some data set that can cause bad performance or cause this growth function to be large, then that's the data set that we're going to be considering with this max right here. So it's because we have this max over all the possible data sets that the growth function and shattering and breakpoints, those are properties of the hypothesis class and not of the data set. Everything that we're going to do in this class is related to having a max right here and thinking about like worst case scenarios or analysis that applies to all possible data points. There are much more complicated analyses that combine both in analyzing the data set and the hypothesis class together, but we're not going into that. Okay, our head's very much buried in the weeds at this point. We're almost through the end of the tunnel though, just a little bit more for us to do. And that's properly define the VC dimension. Once we have the VC dimension, we'll be able to plug everything back into our formulas and for the Hoeffding inequality, and get a version of the Hoeffding inequality, version of the finite hypothesis class generalization theorem that applies to these infinite hypothesis classes. So let me zoom in one more time too, make things a little bit less fuzzy up there. So the VC dimension here, the Vapnik-Chervonenkis dimension, is of a hypothesis set. H is denoted by dVC of H, so this notation right here, or simply dVC. 99 times out of 100, you'll see it denoted just dVC by itself, and only with the parentheses like this if we have multiple hypothesis classes that we need to talk about at once. So dVC is the far more common notation. And it's the largest value of n for which n is exponential like this. So in particular, we saw before that if n is not exponential, I'm going to jump right here to explain things. If mh of n is not equal to 2 to the n, it must be polynomial. And this only happens if n is a breakpoint. The majority of hypothesis classes that we'll look at in this class will have a finite VC dimension, so a finite breakpoint. But occasionally we will see things that have an infinite breakpoint or an infinite VC dimension. And so if the mh of n, our growth function, is always exponential, there is no breakpoint, then we say that the VC dimension is infinite. So in some sense, like I know we've seen sort of 4 different nouns here: the growth function, I guess shattering is a verb, the breakpoint, and the VC dimension here. In some sense, all 4 of those things, they're all talking about the same thing, just in slightly different ways. And if somebody tells you information about the VC dimension, they're also telling you information about the growth function, which also tells you about the breakpoint, which also tells you about whether it's going to shatter or not shatter. It's just sometimes convenient to use one of those terms instead of another, but all 4 of those terms are the exact, they contain the same information inside of them. Let's see. This fact right here is, so yeah, for all hypothesis classes H, we have that the growth function is upper bounded by this term right here, by this polynomial value. And this is something I'm not going to prove in class, but it's just an important fact right here. The textbook proves that, but we'll just state that as an important fact right here. And again, we're bounded by a polynomial, always bounded by a polynomial. The degree of that polynomial is the VC dimension. That's the important thing here. The degree of the polynomial that bounds the growth function is the VC dimension. This can also be stated as that is O of n to the d VC using the asymptotic notation and ignoring the +1 right there. Okay. Let's see, I'm going to keep going and not pause for questions yet. I want to just get to this VC generalization bound theorem. Why did we care about all of this? And the answer here is this theorem. Why do we care? This theorem. This theorem bounds our generalization error, E out minus E in, based on the growth function right here. The intuition behind this theorem, I'm going to scroll up back to the very first page here. The intuition behind this theorem is we take the m here, our size of our original finite hypothesis classes, and we can now replace that m with our growth function, the lowercase m sub h. And when we do that, we get the bound that looks like this, rewritten in 3 equivalent ways right here. The asymptotic notation right here, this version right here is the most important one. The most important version of these bounds. The constant factors in these bounds, like the 8 and the 4, the 2, all these things, they don't really matter. The constants are very loose. So this, as it's written, it is a true statement. There's been a lot of technical work, say like 20 years ago, trying to take these constants and make them smaller. But people have found that not to be particularly useful. So in practice, data mining people, machine learning people, this is the version that we care about and use on a daily basis. We haven't really talked yet about how to use this. That'll be the next couple of lectures, but this is the version that you'll need to memorize for your quiz and that we'll actually use on a daily basis. The log in over here factor, again, so here we have, this is equal to O of DVC log in. I'm just rewriting out this formula over here, over in, minus the log of delta. The log in factor is very small. So log in divided by in goes to 0 very quickly. And so it's common for us to ignore the log factor and just think in terms of without the log factor here. You'll sometimes see people write O tilde like this. O tilde means ignore log factors. And so this statement up here in big O notation is equal to O tilde of square root DVC divided by n minus log delta, like that. And this is what I actually remember, what I actually use in practice. And again, one thing I said 2 lectures ago is that it is the case that this is actually a tight bound. You don't need that log factor, but the textbook doesn't go into how to remove that log factor because it's a very technical thing and it doesn't really matter. So this here is the final thing that you'll definitely need to have memorized to work our problems in this class. Go ahead.
If log of n over n goes to 0 very quickly, then doesn't that also diminish the DVC? Like, doesn't that also bring it down to 0?
Yeah, so the question is, if log n over n goes to 0 very quickly, then doesn't the whole thing go to 0 very quickly? And the answer is yes, the whole thing does go to 0 very quickly, and that is a good thing. For one way of interpreting this theorem, one of the reasons why this theorem is important is because for any finite DVC, so whatever our hypothesis class is, it has some fixed VC dimension that does not depend on the number of data points. So DVC independent or orthogonal to the number of data points in means that as n goes to infinity, as we get an infinite amount of data, then our in-sample error right here converges to our out-of-sample error. So one of the very important facts, implications of this theorem is that as n goes to infinity, our in-sample error converges to our out-of-sample error. And this is something that is only true for things for hypothesis classes of finite VC dimension. Only true if DVC is finite. We will see some examples of infinite VC dimension hypothesis classes in the future, and it will be the case that even though they might be really great on your training error, have in-sample error be 0, there's no way to guarantee that your out-of-sample error will also be low. Because no matter how much data you have, even in an infinite amount of data, if your DVC is infinite, then you're not guaranteed to learn anything. But if your DVC is finite, you are guaranteed to learn something. Sorry, I see some hands up. I want to do we have about just a few minutes left, and I want to do a little fun sort of aside, which will maybe help add some color to this discussion here for us. This here, again, called the VC dimension or in the VC generalization bound after these guys, Vapnik and Chervonenkis. I always think, as I am learning about math, that it is useful to learn about the people who actually discovered these things. And so here's a picture of Vladimir Vapnik, the V in VC dimension. He was born in 1938 in the USSR in Moscow. He co-invented the VC dimension at about 40 years old in the 1970s and 80s. And after the fall of the Soviet Union, he left Russia, and he's still alive. He currently works at Facebook Research. He doesn't actually do anything at Facebook Research. He's just like a really famous person. And so Mark Zuckerberg wanted to pay him a lot of money just to be like a sort of a mascot for them. And I think he acknowledges that that's the case as well. So it's not like I'm saying something bad about him. Let's see. So this is the Vapnik, Chervonenkis. This is Chervonenkis. And I've zoomed in on his obituary here. Yeah. He was, again, also born and raised in the USSR. He stayed around after the Soviet Union collapsed. And just a couple of years ago, I don't have the year on here, like 4 years ago, I think, he was found dead in this swamp right here. Here's a picture of where he was found. At the time, there were a lot of jokes about how he must have done something to Putin, and Putin made sure that he was found dead in a swamp. But he was also 80 years old at the time, and he regularly, his whole life, walked through this swamp. And so it seems reasonable that an 80-year-old person could have something bad happen to them without foul play. This whole theory of VC dimension stuff. So right now I'm just looking at the Vladimir Vapnik wiki page. Was invented in this series of articles right here. So very earliest stuff that we're not even, it's like too old and out of date for the stuff we're talking about to even be relevant at all in the early 1970s. The closest, the thing like where we're actually talking about is from 1995 right here in this book, The Nature of Statistical Learning. So it's only 30 years old. Any other math class that you're taking as an undergraduate, those math concepts are going to be in like the hundreds of years old, like calculus invented in the 1600s, had 400 years for people to think about calculus and what it means. VC dimension here stuff, which is really the foundation of all of machine learning, is only 30 years old here. And so you all are at the front. You're on like the cutting edge of research stuff here. The people who invented this, like this guy, are still alive. Isaac Newton, not still alive, but Vladimir Vapnik, still alive. We're a little bit early here on time. I think this is a good spot for us to stop, though. I realize a bunch of people still had questions. I'll stick around and get those questions answered for you. Otherwise, remember, we do have the quiz on next 2 days from now, next class period, about the chapter 1 material. And so please be prepared for that. I have the office hours tomorrow. If you have more questions about anything, feel free to stop by then. But that's the end of class for today.
Just to confirm, there's going to be no definitions.
No definitions on the quiz on Wednesday. But without knowing the definitions, you can't realistically solve those problems.